Hello everyone, welcome back to Math with Allison. Today we're continuing our series on derivatives. So today we're specifically talking about related rates. Super fun topic, so let's go ahead and dive into it. So we are just going to go into a problem and we're going to solve it together. So our example here is the width of a rectangle is increasing at a rate of 3 centimeters per second. Its length is increasing at a rate of 1 centimeter per second. What is the rate of the rectangle increasing, or the area of the rectangle, when its width is 6 centimeters and its length is 2 centimeters? So our step one is to identify the given information because we want to see what's important. I'm going to zoom in here a little bit. So first off here, we're given that the width is increasing at a rate of 3 centimeters per second. So remember, here's the key word, rate. When the rate is increasing, we're talking about the derivative. And so what we would write is that the derivative in terms of time, so d dt, of the width, our variable here is going to be w, or we can write this as the first derivative of w is going to be equal to 3. So let's look at another piece of information here. We have that the length is increasing at 1 centimeter per second. So again, this is a rate because it's centimeters per second. So we would write that out as the derivative in terms of time of the length, or we could write L prime is going to be equal to 1. Alrighty, so we want to find the rate of the rectangle increasing. And so that means what we want to find the derivative in terms of time of the area, or A prime, the first derivative of area. And lastly, we have one more piece of information here, and it's that we are given information. So we are given that the width is 6 centimeters and that the length is 2 centimeters. So I'm going to write that out. Alrighty, so our second piece is always to try to draw a picture. So I'm just going to draw a picture of a rectangle, right? So when we have a rectangle, we know that we have the length and we have the width. And this picture always helps us visualize it, and it also helps us knowing which kind of equations we're going to work with. So in our case, we know that the area of a rectangle is equal to length times width. And what we want to do in our fourth step is we want to differentiate that. So that means I'm going to take the area in terms of t on both sides. And this is also known as implicit differentiation. So if you like to leave it in terms of dt, you can totally do that. Or if you like to write it with the primes, you can also totally do that. So here on this left side, I'm going to write it as a prime. The first derivative of a is equal to, and actually what we're going to use here is product rule because we have the L, the length, being multiplied by the width. So let me go ahead and set that up. So let's go ahead and take these derivatives. If you like to write it with the primes, we would have that the first derivative of L is equal to L prime. It's not going to be 1 because we're taking the derivative of L in terms of t. So those are two different variables. If you like to write it with your dt's, this would be d dt of L. Otherwise, with your primes, totally fine. So similarly, our g prime is going to be w prime, or if you like, you can write it as d dt of w. I'm going to go ahead and use the primes because that's what I like to see visually. And with product rule, we're going to go ahead and multiply them across and add them together. So we get L prime times W, and then we add L times W prime. And so now that we have the derivatives written out, I'm going to rewrite it the other way with the dt's just in case. We are going to plug in what we know. So let me zoom out here just a little bit so I can highlight what we know. So like we talked about earlier, we already know that the width is going to be a value of 6 and that the length is going to be a value of 2. And then we have that the derivative of L, or L prime, is equal to 1. So we can fill that in right here. And that also we have the derivative of W, or W prime, is equal to 3. And remember that this A prime, this derivative of A, that is what we wanted to find, right? That is what we're trying to solve for. So let me go ahead and plug in these values. Alrighty, so I'm going to go ahead and perform that math. So this becomes 6 plus 6, which is equal to 12. And so our last step is to write it out nicely. So here I would write it out. So this is my super nice answer. In order to find the measurements, I just went back to the top and we were talking about centimeters per second. And so I know area is going to be centimeters squared per second, or the derivative of the area. And yeah, so let's go ahead and see some more examples of this. I don't have the steps laid out perfectly for us, so we're going to try to do that together. So we have an oil rig springs a leak in calm seas. Sad face, we don't like when that happens. The oil spreads in a circular patch around the rig, and the radius increases at a rate of 30 meters per hour. How fast is the area of the patch increasing when the radius is at 100 meters? So what people sometimes like to do first actually is draw a picture. So if I were to draw a picture, I know that it's increasing in a circular fashion, so I'm going to have a circle. So let's pretend this in the middle is the rig, and we are given the rate that the radius is increasing, right? And we want to find how the area is increasing. So let's write down our formula. The area of a circle is equal to pi r squared. And that's what we're going to use to differentiate, but let's go ahead and look through our important information. So we have that it's spreading in a circular patch, and the radius is increasing at a rate of 30 meters per hour. And so we have that the derivative in terms of time of the radius is going to be equal to 30, which if we like to write it with primes, that's going to be r prime. And we also have that we are given a piece of information that the radius is exactly equal to 100 meters. And so here we have that just normal r is equal to 100. And let's see what we're trying to find. We're trying to find how fast the area of the patch is increasing. And so the area of the patch is going to be the derivative of a, or the area, or a prime. And so that is what we want to find. So let's go ahead and use implicit differentiation. I'm going to take the derivative of both sides in terms of t. So we know the derivative of area is just going to be a prime, right? And here on this right side, what I'm going to do so I don't get confused is I'm going to take out all my scalars. So remember that pi is just a number. It's just a constant. And so we don't have to worry about that when we're taking the derivative. We're going to focus on taking the derivative of r squared. And actually, remember, r is different than t, so the derivative is not going to be super nice. And we're going to set that up using chain rule, actually. And so my inside u is going to be r. And that means my outside is going to be u squared. That's going to be the power of 2. And so now when I take the derivative of r, I get r prime. And when I take the derivative of the outside, I get 2u. So let's go ahead and plug that in. So I get a prime is equal to pi times. Now I get u prime, so r prime. And I'm going to multiply that by g prime of u. And I'm going to plug u back in, so I get 2r. So when I write that out nicely, I get a prime is equal to pi times r prime times 2r. So let's go ahead and fill in what we know. A prime is what we're looking for, so that's going to stay the same. The pi doesn't change also, but r prime, we're given that it's increasing at a rate of 30 meters per hour. Multiply by 2 times, and let's fill in what r was, and this was when r is at 100 meters. So, and then we just go ahead and use math. So when I do that, I get 30 times 2 is 60 pi times 100. So I'm going to multiply 60 and 100. A prime is equal to 6,000 pi. I'm not going to multiply what pi is equal to because that's going to give us a big long number and I don't want to work with that. So now I'm going to go ahead and write this out all nicely. Alrighty, so I have that written out all nicely here. The area of the patch is increasing at a rate of 6,000 pi meters squared per hour when the radius is 100 meters. Alrighty, we have one more example here, and we're going to use some trig, everybody's favorite. So we have an observer stands 200 meters from the launch site of a hot air balloon. The balloon rises vertically at a constant rate of 4 meters per second. How fast is the angle of elevation of the balloon increasing 30 seconds after the launch? So we have a beautiful drawing right here. We have our person is standing 200 meters away from the launch site, and that it's rising vertically, and so that's the value of y. And then that little point on top is a hot air balloon. So let's go ahead and pick out important pieces of information. First, we have that it's 200 meters away, and so we already have that value in there. The balloon rises vertically at a constant rate of 4 meters per second. And so that means my derivative of y, or d dt of y, this is equal to y prime, is going to be 4. Now we want to find how fast the angle of elevation is increasing. And so what this is talking about is this value of theta right here. So we want to go ahead and find the derivative of theta, or we can write theta prime, and that is what we want to find. We have one more piece of information right here, and we're working with the fact that this is going to be 30 seconds after the launch. And so I'm going to have that my time is equal to 30 seconds, right? Okay, so let's go ahead and think of an equation for a drawing. I know that I have the opposite and I have the adjacent legs of the angle. And if we remember SOHCAHTOA in terms of trigonometry, TOA is going to be tangent. So I'm going to write that out. We have tangent of theta is equal to opposite over adjacent, which is going to be y over 200. And so now let's go ahead and differentiate this. So I'm going to take the derivative of both sides in terms of t. Alrighty, let's do this thing. So first we're going to take the derivative of tangent of theta. I'm going to use chain rule, right? And so I set my inside equal to theta, and I set my outside equal to tangent. When I find my derivatives, I get theta prime, or the first derivative of theta, and then g prime of u, this is going to be secant squared of u. So when we plug that in, I get theta prime times secant squared of theta, and this is going to be equal to, and remember, when we take the derivative of y, that's just going to be y prime. So this becomes y prime over 200. That 1 over 200 is just a scalar, it's a constant, so it just hangs out. Let's go ahead and look at this and think about what we know and what we want to find out. So theta prime, or the first derivative of theta, that is what we wanted to find, right? So that's totally fine staying by itself. It looks like we also have a y prime, which is equal to 4, but our issue is, what is theta equal to? And actually what we're going to use is another equation. So we have that t is equal to 30 seconds. So what is our value of y when t is equal to 30? Because remember, it is rising at a rate, it's rising at a rate of 4 meters per second. Well, that means I can find how tall it goes after 4 seconds, right? 4 meters per second times 30 seconds, that is equal to 120 meters. And so I get my y value is equal to 120. So I'm just going to go ahead and fill this in on my triangle right here. And now this tells me I can actually find theta, and I can find theta using the same process. So I know tangent of theta is going to be equal to opposite over adjacent. So here I get 120 divided by 200. And if I want to get theta all by itself, I take inverse tangent of both sides. So I get inverse tangent of 120 over 200. I'm going to go ahead and use Desmos to find out what that value is equal to. Okay, in terms of radians, because that's what I'm working with, I get 0.54, and we'll leave it at that. So this is going to be 0.54 radians. And so now I'm going to go ahead and rewrite the equation that we have. So let's go ahead and fill in some things that we know now. I know theta prime is what we're solving for, so I can leave it, and we get secant squared of 0.54 radians is equal to y prime, which is 4 over 200. So let's go ahead and calculate some of those values. So I get secant squared of 0.54 is equal to about 1.36, and this is equal to 4 divided by 200, and as a decimal, that is equal to 0.02. So in order to get theta prime all by itself, I'm going to divide over that 1.36. So this is about equal to 0.015. I did some approximating, and this is going to be radians per second. So now we found the rate that the angle is increasing. So let me go ahead and write that out all nicely. Awesome. So this is all I had for us today. If you enjoyed this video, I have many more like it, so make sure to check out my playlist. They're linked down below. Otherwise, please give it a thumbs up and comment other topics or problems you'd like to see done. Thanks for watching.